This is an introduction to Chapter 11 on vibrations and waves. So we're shifting gears considerably from what we've been studying with motion. Now we're switching over to waves. So think about waves that you observe in the everyday world around you. Maybe waves in water, sound waves, light waves. Think about exactly what is traveling in a wave and what a wave transports. If we look at some animations of waves, in the top one you've got people doing the wave. In the middle one you've got a wave traveling through matter. And in the bottom one you have a wave traveling along a string. Think about the particles and observe the particles in each one, and notice how the particles themselves move. And then consider how the wave moves. For the top one, with the people doing the wave, the people oscillate up and down, but the wave travels from the left side of the screen to the right side of the screen. Similarly, in the other two simulations, in the middle one, if you look at one of the black dots representing a particle, it oscillates a little bit, in this case to the right and then back to the left, but it doesn't really go anywhere. The wave disturbance itself moves from the left side of the screen to the right side of the screen. And similarly with the wave and the string, the individual parts of the string are going to go up and down and then go back to where they were, but the wave itself moves across the screen. So then if we consider defining a wave is a disturbance in the particles in matter, such that the particles oscillate, but they go back to their original position, and the wave itself travels, or it's a disturbance that transfers energy, and it uses the particles, but the particles themselves don't end up going through any net displacement. Again, key things to remember here. Your particles oscillate, but don't really go anywhere. They return to their original position. Just like people doing the wave, you stand up, you sit down, you're back in your seat. You didn't move anywhere. However, energy itself is transferred. So wave transfers energy and uses matter sometimes. Sometimes it doesn't. But it transfers energy and not matter. Now, let's describe waves in terms of different characteristics of waves. And these are things that should be reasonably familiar to you if you have pondered waves in math class. So if we consider a wave here, we can describe the wavelength of a wave from one crest to the next crest, or from one trough to the next trough. Both of those would constitute a wavelength. Now, in defining a wavelength, it is not descriptive enough to say that the wavelength is the length of a wave. The wavelength is specifically a distance measurement. It is the distance from one point on a wave to the corresponding point on the next adjacent wave. So that would be crest to crest, trough to trough, any one point to the next corresponding point, and that distance is the wavelength. Now, our symbol for wavelength is a Greek letter, lambda. Looks like an upside down Y. And your units of wavelength would be meters or centimeters. We can also talk about the height of a wave, okay, or that distance from equilibrium out to maximum displacement, and that's known as the amplitude. Now, symbol for amplitude, we'll just use a capital A, and it's also going to be a measurement that is in meters. So I'm going to mark the A's. I'm going to go back and mark the wavelengths. Now, other things that we can measure in terms of a wave, let me get us some more room here. Would be the frequency of a wave. And closely related to that would be the period of a wave. Frequency of a wave, that is the number of waves passing a point each second. So then your symbol for frequency is a lowercase f, and your units then would be waves per second, sometimes oscillations per second, and a wave per second is called a hertz. And hertz is abbreviated typically Hz. Period is very similar to that, but it's the inverse. So instead of the number of waves per second, now time is on the top. This is the time for a complete wave. To pass a given point. So then this is time for a wave, symbol capital T. So then this would be in units of seconds per wave. However, a lot of times this is just expressed in seconds. Pardon me. Now, these are inverses of each other. So then waves per second, seconds per wave. So then mathematically we can write T is equal to 1 over F, or you can invert one of these to get to the other one. Now, let's also talk about wave velocity. And this is no different than how we've dealt with velocity before. This is basically how fast a wave is traveling. And that will have a given direction with it. Symbol for velocity is still v. Units of velocity are still meters per second. Okay, now if we consider calculating wave velocity, we can use our velocity equation we introduced way back in chapter 2, displacement over time. If you know how far the wave travels, it travels across the classroom, and you know how long it takes to, for example, travel across the classroom, then you can divide those two. We can also write this equation based on the variables we defined above. If our how far is one specific wave or a wavelength, then the time for one wavelength would be the period. So we can also find velocity by wavelength divided by period. Being that period and frequency are inverses of each other, if I plug in a 1 over f for t and then invert, I also get wave velocity is frequency times wavelength. So any of those methods will work in terms of calculating wave velocity. It just depends on what you know. Ponder physics.